In this lecture, we're going to study a particular outage that happened at the Amazon Web Services, the AWS service. So this outage occurred April 21st, 2011, and all the data and all the information we are going to see in this lecture are from a postmortem analysis that AWS published after this outage was resolved. Once again, our goal in discussing this outage is not to say that AWS is a bad infrastructure. In fact, it's quite the opposite. AWS was very open and honest and transparent with its customers and users, and they kept giving continuous updates during the outage. And after the outage, AWS improved its infrastructure to avoid outages like this. And as you know, AWS continues to be one of the market leaders in the cloud computing area. During this outage, several companies using AWS, especially the EC2 service, Elastic Compute Cloud, went down. This included companies like Reddit and Foursquare. AWS dashboard showed problems with the EC2 service and also other storage services. As you'll see, the EBS service was the one that was the root cause of this outage. The overall outage lasted at least 3.5 days. There was also a long tail of recovery and some permanent data loss for some of the customers. So a little bit of background before we discuss the actual outage itself. AWS is split into regions. You can think of these regions as being separate data centers. For instance, there is a US East 1 region, there's a separate region called US West 1, and so on and so forth. Typically, customers who are running a service for their users want to run their service in a region that is close to some of their customers. So if you have a service that is running on the East Coast, you might want to host it on the US East 1 region. Each region itself is divided into multiple availability zones. The best way to think about it, the availability zones, is like there are different racks within the same data center. Okay, so you can have automatic data replication across availability zones within a region, but this has to be explicitly done by the customers, and not all customers choose to do it. Okay, and the outage here that we'll see affected a lot of customers that did not choose to do it. The outage really affected the AWS Elastic Block Storage Service, or EBS, which essentially is mounted storage devices that are accessible from the EC2 instances. So think of these as large volumes of data that are being stored, that EC2 instances, VMs, virtual machines are accessing them as they're running the service. Now in AWS, a single EBS volume runs inside an availability zone, and it uses two networks. A primary network that is used for EC2 and EBS control plane traffic. When I say control plane traffic, I mean basic operations like create a volume, close a volume, open a volume. This is as opposed to data traffic, which actually transfers the real data that is stored in that volume. Control plane traffic is relatively less in volume compared to the data plane traffic, but it is very, very important. So anyway, a primary network is used for EC2 and EBS control plane traffic, and a secondary network is used for overflow. The secondary network used to be over-provisioned when this outage happened, used to be over-provisioned with a lower capacity, because the only goal of having it was to catch some of the overflow traffic. If the primary network was full, then you would overflow some of the traffic to a secondary network. The control information is replicated across zones. This is for availability of the control information. And this includes meta information about the volumes, where they're stored, how much data is stored in them, but not the actual data itself. That's what I mean by control information. The EBS volumes are replicated for durability, and each volume has a primary replica. Whenever one of the replicas is out of sync, or when there is a node failure detected, the replicas are programmed to do aggressive remirroring of data, at least before this outage happened, which means that if the primary discovers that one of the backups is gone or missing or is not responsive, it will try to aggressively create another backup because it doesn't want to lose data if another failure happens at the primary. So here is the outage timeline itself. At 12:47 a.m. there was a routine primary network capacity upgrade that was supposed to be done in the availability zone in the US East region. The traffic was shifted off several primary network routers to other primary network routers. So far, so good. This was as intended. However, the critical error was that one of the operators involved in this capacity upgrade shifted traffic for one such router to a secondary network router. Remember that the secondary network router has very limited bandwidth because it's only for overflow. But when you shift the entire traffic from a primary network router to a secondary network, then the secondary network is going to be overloaded and is going to be overwhelmed with traffic. As a result, a lot of these packets and messages are going to get dropped, and several EBS volumes will now not be able to communicate at all with their primary they don't have any primary network, right? So this means that the primary network is disconnected, the secondary network has low capacity and overwhelmed, and many primary replicas have no backup. The team quickly discovered this critical error after it started happening, and you might think that at this point the outage will start to recover. But as you'll see with outage case studies, outages keep cascading because of other reasons that come into play as well. In this particular case, after the team rolled back the critical error, the outage had already been triggered. Many primary replicas thought that they had no backup. These automatically started remirroring aggressively because they thought, well, there's no backup, and if another failure happens at me, then the data might be lost, so let me try to create another replica. And this was happening at all the affected EBS volumes that were on that particular primary network. So all at once, the free network capacity was quickly used, and replicas were creating more traffic where they were trying to remirror the data. This overwhelmed the network even more and made things even worse. So you can see how this cycle is a cascading loop of very, very bad things leading to even worse things. And this is what is known as a remirroring storm, which affected about 13% of the EBS volumes in AWS. When the network was unavailable for the control plane traffic, this meant that it was unable to serve create volume API requests for EBS, which meant that new volumes could not be created. And so a lot of these control plane operations like create volume requests started to back up. They started to have a long timeout, and they started to build up in queues. When the thread pool filled up, the control plane started to reject these create volume requests, and this is where the customers and the users really started to see the outage affecting the service that they were trying to access or run. At 2:40 a.m., this is again at morning, the AWS engineers are working hard to resolve this outage. The team disabled all new create volume API requests. And at 2:50 a.m., within a few minutes, all error rates and latencies for the EBS APIs start to recover. They start to go down. Again, you might think here that the outage is starting to end here, but once again, cascading causes come into play. Two issues made things worse. The first is that primary searching for potential replicas did not back off. When they tried to create new replicas, they overwhelmed the network with traffic. This meant that they could not create new replicas. But the way the primaries were programmed was that they would try equally hard or harder to create that backup replica when they failed the last time. They did not back off, which meant that they did not wait for a longer time to make their next attempt of creating the backup. Okay, so this made the system much worse because it overwhelmed the network with data. Also, a race condition had been known to exist in the EBS code that was only triggered by high request rates, and this was exactly one of the situations where you had very high request rates, and so this caused even more node failures. So at 5:30 a.m. that morning, error rates and latency started to rise again, and the engineers had to grapple with this again. So once again, a little bit of background here. The remirroring is essentially a negotiation between an EC2 node, an EBS node, and the EBS control plane. This renegotiation is required so that you ensure that there is exactly one primary for each volume. Due to the race condition, EBS nodes started to fail, and the rate of these negotiations increased, and this affected the EC2 nodes as well. This caused even more node failures, and therefore it again caused the rate of negotiations to increase, and you can see how this cycle is a cascading loop of things getting bad and worse and worser. This resulted in the brownout of EBS API functionalities. A brownout is essentially where you don't have a blackout. It's not that the outage completely takes EBS out, but the operations are pretty unreliable. The brownout term comes from electric power, where instead of having white light, which is normal light, you'd have brown light when the voltage goes below the recommended voltage. So something similar happened in the EBS because of this outage. So at 8:20 a.m. in the morning, the team started disabling all communication between EBS cluster in the affected availability zone and the EBS control plane. The availability zone was still down and unresponsive or very slow, but the control plane started recovering slowly. At 11:30 a.m., the team figured out how to prevent the EBS servers in the affected availability zone from doing this aggressive, futile remirroring where they were not able to create any backups. And the availability zone started to recover at this point of time. Customers still continue to face high error rates for new EBS-backed EC2 instances until noon. New instances that were created with new EBS volumes still suffered fairly high error rates. And one of the reasons for this was that another new EBS control plane API had recently been launched. That was for attaching new EC2 instances to volumes, and that had some error rates and some bugs which were being hidden earlier by the outage, but that the engineers were seeing now that the outage was starting to get resolved. So again, these are other causes that come into play that keep the outage going on and on. So by noon, however, the good news was that no more volumes were getting into the stuck state, but 13% of the volumes stayed in the stuck state, meaning that they were not really accessible and they were not able to create the backup copies. There was a pretty long tail of recovery for this particular outage, and you can read more details about this on the post-mortem report. By noon, April 24th, which is several days after the outage, all but about 1% of the volumes had been restored. So 99% of the volumes that were affected had been restored. Eventually, 0.07% of the affected volumes could never be recovered, and the data was lost permanently. Amazon Web Services did give credit to these affected customers, not just the ones who lost their data, but also the ones whose service was unavailable for a significant period of time. This outage affected not only EC2 and EBS, but also affected the relational database service, also known as RDS, especially the ones that were single availability zone. So what are the lessons we learned from this particular outage case study? First, outages or failures that are large often start with a human error. In the AWS case, the human error was the operator moving the entire traffic from a primary network to a secondary network. And the secondary network was never intended to take over for the primary network. It was only intended to be an overflow network. But that's not the only reason why the outages keep going on. They keep going on, or they balloon, because of cascading other failures that happen in the system, which may or may not have anything to do with human error. For the specific case of AWS, this outage could have been avoided in some ways. First, if the network reconfiguration processes had been audited well to create, for instance, a step-by-step protocol for upgrades, and if the operator had followed these steps one by one, then perhaps the mistake that triggered the outage of moving data, all the data from a primary to a secondary network, that mistake would never have happened, perhaps. They could have had the secondary network not just be an overflow network, but instead have enough capacity to take over for a primary network. That would also have prevented the outage. The remirroring storm really kept the outage going, and if primaries had backed off, meaning that if they tried to create a backup, and if they fail, then they wait for slightly longer than the last time around to make their next attempt at creating the backup. Okay? If the primaries had backed off, then the remirroring storm would not have happened. Everyone would have played nice with each other, and the outage would not have kept cascading. The race condition also kept the outage going, so fixing it ahead of time might have prevented the outage from going on as long as it did. Users who wrote code to take explicit advantage of multiple availability zones were not affected as much by this outage as users who just had data on one availability zone. Also, throughout this outage, AWS kept giving continuous updates to its customers and its users and their users. But in general, AWS used this as an incentive, as a catalyst to design better dashboard communication tools. And if you go to AWS, you will find such dashboard tools that give the health of each one of their services. The same is true for other cloud providers too, like Google and Microsoft Azure and so on and so forth. AWS also gets service credits for its customers that were affected by this particular outage.